SOCAMM speeds up the traditional HBM method using a serial process. This is its main idea. When combining multiple chips in 2.5D or 3D stacking, the number of pins must be reduced. NVIDIA is developing NVLINK, NVSWITCH, and InfiniBand to support these advancements. Greetings everyone, this is Era speaking. Recently, NVIDIA reached out directly to the local memory industry. At the moment, we are engaged in discussions about SOCAMM, which is an innovative memory technology that appears to have the potential to replace HBM. Earlier this year at CES, there was an announcement about collaborating with the memory industry while introducing a proprietary standard called DIGIT for AI computing systems designed for general PC users. The name SOCAMM is quite peculiar, isn't it? Unlike HBM, which stands for High Bandwidth Memory, SOCAMM doesn't immediately reveal its purpose. While not much is known about it yet, from a technical and engineering standpoint, if our goal is to boost memory bandwidth and create something efficient for PCs, SOCAMM might just be the next big thing to replace HBM. What kind of cutting-edge technology could be behind this? I have gathered some information that will help you understand SOCAMM better, including its overall memory bandwidth, and why it is ultimately significant in the context of AI. Through this information, you will be able to gain insights into what makes packaging technology so fundamentally important in this field. Ultimately, this involves AI connecting multiple GPUs together, or alternatively, for powerful computing, it is essential to have memory that offers not only sufficient bandwidth, but also low latency and extremely fast response times, isn't it? In the end, advancements in AI and high-performance computing are hitting roadblocks with existing memory interfaces like DDR5 and even HBM. Therefore, we are crafting our own proprietary standards to make a bold entry into both the personal PC and AI PC markets, demonstrating our dedication to cutting-edge innovation and top-tier performance. SOCAMM is a type of memory designed to be integrated into personal computers, providing extremely low latency. This means that when data is fetched, it reacts almost instantaneously, much quicker than conventional memory. It appears that NVIDIA is working on a memory standard that can be mass-produced independently, which might be simpler to manufacture compared to high-bandwidth memory. While keeping in mind the goal of achieving both low latency and high performance, let's discuss the rules and principles that need to be established to make this possible. Now, what NVIDIA is referring to here is something called SOCAMM. So what exactly is this SOCAMM? It's essentially a combination of what is known as SO-DIMM and another technology referred to as CAMM. You can think of it as a combined standard. To be precise, it's not just a mix of standards. It would be beneficial to understand it as a structure that combines the advantages of the CAMM standard with those of the SO-DIMM standard. SO-DIMM, which stands for Small Outline Dual Inline Memory Module, refers to a specific type of module that is typically used in computers for inserting DRAM. This module generally connects directly to the computer's motherboard. There's a designated slot for memory, known as DIMM, which stands for Dual Inline Memory Module. However, there's a smaller version known as Small Outline. It's about half the size. If you take a look, you often see these DIMMs, right? They are commonly plugged into PCs. But this one is only half the size. There exists a structure known as SO-DIMM, which is designed to be easily attachable and detachable from the system. Moreover, there's something called CAMM, which is a separate standard developed specifically as a low-power, high-performance memory solution. Have you seen this before? It's not widespread yet, but efforts to integrate it have been ongoing for a couple of years. As technology progresses, sticking to outdated standards no longer delivers the required performance. Due to excessive heat generation and other factors, the communication protocol between RAM and the PC, specifically the motherboard and CPU, needs to be redefined. This involves establishing new standards for host communication protocols, and one of these new standards is known as CAMM, which is an integral part of this redefinition process. NVIDIA is exploring a new memory technology known as SOCAMM, which integrates the features of low power consumption and high performance with the flexibility of a detachable SO-DIMM structure. Keep in mind that their aim is to harness these advantageous traits to develop an innovative and groundbreaking solution, which is their primary focus at this stage. So what are the main objectives of SOCAMM? The first is to achieve high bandwidth. When we mention HBM, we're talking about high bandwidth memory. To handle AI workloads effectively, memory can often become a bottleneck. Even if the GPU operates at high speed, slow memory can still hinder fast processing. In other words, to process AI, high memory bandwidth is essential. To put it simply, it's about the speed at which data is transmitted. When we look at enhancing transfer rates, We aim to achieve speeds that are even faster than traditional DDR5 or HBM. This means sending data at incredibly high velocities and ensuring that the memory can be accessed and respond almost immediately. This is what we call latency. You want to reduce it, right? This gives it SOCAM characteristics. What did I mention earlier? I said SO-DIMM, right? The core aspect of SO-DIMM is that it's half the size of DIMM. While this is a notable feature, the key point is that both DIMM and SO-DIMM can be attached and detached from the motherboard. However, if you look at HBM, it's not detachable. TSMC's CoWoS technology, which integrates Hynix's HBM with NVIDIA's GPUs, like the Blackwell or Hopper, utilizes an interposer to ensure a seamless and permanent connection. This means that these components are not designed for detachment. Instead, they are firmly and permanently bonded together on a silicon wafer, creating a single cohesive unit. Here we have an illustration of HBM. When paired with a separate GPU, the concept is to connect these two elements onto a broad board, merging them into a single cohesive unit. Because this design is non-detachable, any single error means the entire unit must be discarded, resulting in low yield rates. In the PC market, where many consumers are adopting AI PCs, non-detachability can lead to significant issues. Therefore, efforts are being made to ensure these components are detachable. From this perspective, the primary consideration is high bandwidth, followed by, in the context of detachable components, NVIDIA has introduced an innovative approach to merge memory and GPU into a unified unit, thereby enabling easier detachment. This idea, which aims to streamline the detachment process, is known as core package memory. We often talk about processing in memory or computing in memory, don't we? Ultimately, GPUs and other processing units need to be positioned right next to the memory for rapid processing, and they must also be designed to be detachable. To achieve this, instead of using an interposer to connect separate dies of HBM and GPU, they have adopted a method that integrates them into a single unit through advanced 3D stacking techniques. They are considering packaging the components together as if they were a single unit. The third important aspect is that this core packaging must be detachable. In a broad sense, traditional 2.5D package cores are also considered core packages. However, the goal here is to integrate everything into a unified structure. Why pursue this integration? The main objective is to significantly reduce the physical distance between the GPU and memory. When operating a processor, numerous connections link these components, both within and outside the unit. These connections draw a considerable amount of power, leading to high energy consumption. So the placement and routing, P&R process, which involves arranging components and connecting wires, is crucial. Even if the design is logically and programmatically sound, improper placement can lead to significant heat issues. To integrate the core into a single unit, we need to create TSV holes and ensure the wire lengths are kept very short. In this context, it becomes essential to revisit HBM and understand its significance once again. Now, if we think about whether HBM or high bandwidth memory has met these demands, we can observe that it employs an interposer to link the memory and logic, facilitating ultra-fast data transfers and achieving low latency. The TSVs, which you can see here, act like elevators connecting the layers of high bandwidth memory. Imagine memory chips stacked like floors in a skyscraper, with an elevator system designed to move data swiftly between levels. This is how traditional HBM is manufactured, creating a 3D structure that allows signals and currents to travel directly through silicon pillars. It's akin to taking an elevator in a high-rise building for the quickest journey down. This significantly reduces latency and minimizes signal loss as much as possible. However, now we arrive at the highlight of today's discussion. The HBM technology, which stands for high bandwidth memory, ultimately operates using a parallel processing approach. Imagine it as a structure with multiple layers of elevators, each capable of sending down 1024 or even 2048 data units simultaneously in parallel. This allows each piece of data to be transmitted independently. Think of it like a highway with numerous lanes, which allows for a large volume of cars to travel at once. Similarly, this technology is designed to send data in parallel. We want to send as much as possible in parallel. Also, keep the physical distance short. That's one way to look at HBM. By sending data in parallel, we aim to shorten the physical distance. But now, we're seeing stacks with 12, 16, or more layers, and they keep growing, right? When aiming to deliver significantly higher bandwidth with lower latency, physical limitations can arise. This is an ongoing area of research. In the AI PC market, where the goal is to provide an AI PC for every individual, if the yield is as low as HBM, it becomes impossible to fully leverage its capabilities. This means production efficiency will be compromised. In that sense, you have this interposer in the middle of the existing HBM structure, right? In this setup, an interposer is paired with a GPU and an HDM is placed nearby. It is well known that the yield rate of the HDM can drop significantly. As we start integrating the interposer with the GPU and the HBM, the yield rate may decrease for each component. When these individual yield rates are multiplied together, the overall yield rate, even if each has a 90% yield rate, when you multiply 99, 81, and 81 by 9, the yield rate drops to around 70%. This means that with the current AI data centers already experiencing bottlenecks, the existing HBM might not be sufficient to support a world where 75 people live together and AI PC needs to be distributed. This isn't an obvious fact, just my personal opinion. Please don't consider this as the ultimate answer. I highly encourage you to share your own opinions as well. However, from my point of view, it seems highly likely. So, the next crucial concept we need to delve into is HBM, which fundamentally possesses a parallel structure. Moreover, it features very short paths, and these two aspects are essential for achieving high bandwidth. However, the third issue is that the yield rate can drop significantly when manufacturing these. This means relying heavily on TSMC. These factors make it hard to produce memory independently, which is known as SoC. So let's take a closer look at SoC. In my previous lecture, I was the first YouTuber to cover SerDes related content while creating the Broadcom video. I mentioned serializers and deserializers. Actually, I have acquaintances at Broadcom. SerDes is a technology that's extensively used in system-on-chip design. Broadcom is very good at making SerDes, and NVIDIA also excels at it. By integrating SerDes into what we call system-on-chip, it can replace the traditional parallel high-definition multimedia approach that has been widely used. I assume that the method of manufacturing serially in a straight line to make it quickly is what SoC is all about. Originally, it was done in parallel. With HBM, serialization isn't necessary. You can just transmit it immediately. Sending data in parallel is faster, right? Why not just send it like that? So what does serial mean? In terms of time, this sends 8 units per second. But this one sends only 1 unit per second. So wouldn't serializing make it slower? You might think this way, but instead it requires 8 physical pins. When we talk about pins in the context of semiconductors, we are referring to those small ends, right? Each of these ends, or pins, has to be physically prepared to allow different signals to go out separately. However, with serialization, it is possible for the signals to be sent out through a single pin. So what's the advantage? When this happens, errors occur during data transmission. Why? When we mention these 8 pins, it's important to note that each pin is linked to its own dedicated signal line, right? When the number of signals becomes too high, they start to interfere with each other, mix with noise, and experience crosstalk, causing the signal integrity to degrade. This is referred to as signal integrity, and when it's not maintained, errors persist. On the other hand, if you serialize and send the signal through a single pin, the signal enters more cleanly, allowing you to send 2, 3, or 4 signals per second, rather than just 1. Overall, as the number of I/O pins decreases, even if we make semiconductor chips, the number of pins on the chip itself that goes into the AI PC will decrease. This reduction in pin count will also simplify printed circuit board design, effectively minimizing the space required. While I used 8 pins as an example, the actual number could be in the thousands depending on the configuration. By employing a serializer to convert the data into a serial format, we can maintain signal integrity, thus facilitating high-speed data transmission. Therefore, when you combine the serializer and the deserializer into a single unit, to be precise, this is called SerDes. Do you understand what I mean? Therefore, it has been revealed that these SoCs are being integrated through co-packaging. Imagine combining AI and GPU logic with memory modules from different manufacturers into one package and stacking them in 3D. They would need to be very close to each other, right? So wouldn't it be like using HBM? You might see it this way, but when you combine multiple chips in 2.5D or 3D, the number of pins they have needs to be significantly reduced. Originally, GPUs like Hopper or Blackwell had separate chips connected using interposers. Even with a large number of pins like 1024 or 2048, they could be connected using silicon wafer routes. This worked despite the significant physical distances. But let's say we integrate them into a single chip. In this narrow space, many paths need to be created. Instead of relying on the high bandwidth memory, HBM approach, which distributes data across multiple channels, leveraging SerDes technology to serialize data and then transmit it at high speeds proves to be more efficient. The advantage of SerDes, often recognized as an intellectual property, IP module, is particularly evident in this context. Modules equipped with these capabilities typically support a variety of protocols, including PCI Express, Ethernet, and InfiniBand. NVIDIA is currently developing its own SerDes technology to ensure compatibility with NVLINK, NVSWITCH, and InfiniBand. Broadcom has also excelled in this area, enabling the creation of customized AI chips. Of course, using SerDes to significantly increase I/O speeds similar to HBM might also have the drawback of generating a lot of heat. In AI applications, there's an immense amount of computation that requires frequent memory access. Even if we shorten the routes and drastically cut down the number of I/O pins using SerDes, these issues won't just vanish. It's plausible that memory manufacturers are currently in discussions on how to tackle this, from the standpoint of core packaging. Secondly, with core packaging, what happens is that there's no room, no space left. Because there isn't any space available, the third step is to reduce the number of I/O pins significantly. But how did they approach this challenge? Traditionally, we used parallel HBM and interposers, but by adopting SerDes, we can significantly reduce the number of pins and achieve ultra-fast data transfer through a single pin. This method also enhances signal synchronization, which is essential for efficient communication, as parallel signal paths can lead to physical separation and timing issues. Even if we start sending data at the exact same time, some signals will arrive faster while others will be slower. This is what we call synchronization. Synchronizing clocks requires additional steps due to slight timing differences, often referred to as clock skew. Addressing this skew can be quite complex, but utilizing SerDes can potentially avoid these issues. Although it might seem that integrating SerDes IP adds complexity, it actually streamlines the design by reducing the number of I/Os. If you only need one or two, the PCB itself will shrink, and it's not just about the pins, right? It needs many connections inside. Imagine everything inside being linked. When there are more pins, the complexity increases significantly. On the other hand, having fewer pins means the PCB design will be simpler with fewer lines, resulting in less complicated wiring. This is particularly beneficial for personal PCs and AI applications, as it can improve efficiency and performance. Therefore, I believe this approach holds significant promise. NVIDIA has greatly benefited from using SerDes technology, particularly after acquiring Mellanox. This acquisition allowed them to implement NVLINK, which facilitates extremely fast, high-speed data transfers between GPUs through efficient serial communication using SerDes. PCI Express also enables communication within data centers. When multiple nodes need to interact, NV switches are used. By integrating SerDes with NV switches, data is transmitted quickly in a serial manner. Within the GPU, the HBM and GPU previously communicated rapidly in parallel. However, by enhancing the SerDes design, we now achieve even faster serial communication. Essentially, SerDes acts like an additional highway in core packaging, significantly reducing congestion while maintaining short distances and fitting numerous components into a compact space. So what we're really curious about is this. When this new technology becomes available, won't it have the potential to replace HBM? However, this approach has a different focus. If it had been feasible to do it well from the beginning, we would have taken that route. Instead, this method scales down and optimizes SerDes to create separate memory. Consequently, what we see now is that HBM is projected to grow significantly, especially in the third and fourth quarters of 2025. This implies that the revenue will increase. While there is still demand for HBM at the center of data centers, HBM has been increasing bandwidth based on parallel interfaces. On the other hand, SoC is being discussed in terms of co-packaging, which combines a CPU and a GPU. In this context, the method to achieve high bandwidth is inevitably, in my opinion, employing SerDes is likely the only viable approach. Nonetheless, while SerDes can enhance the performance of HBM in server GPUs, HBM itself is already optimized for swift deployment. Despite its notably low yield rate, HBM, when paired with large-scale GPUs, relies on air or liquid cooling systems to maintain optimal operating temperatures. Given its own level of optimization, it is expected to come in a detachable package that is more compact yet retains high bandwidth. If this system on chip becomes a reality, prototypes have reportedly been in testing for 2 to 3 years. Therefore, it is anticipated to be utilized not only in server graphics processing units but also in high-performance computing, laptops, and artificial intelligence personal computers. It appears that NVIDIA might be leading the charge in this area. However, the more critical point is this. I don't see memory companies having a dominant position in the semiconductor market just yet. There's a lot of discussion about memory being the bottleneck, which could potentially allow memory companies to exert significant influence over companies like NVIDIA and Intel. There is a lot of discussion about memory, and companies like NVIDIA are directly reaching out to South Korean giants such as SK Hynix and Samsung Electronics to collaborate intensively and enhance performance. I believe our memory companies should assert their leadership in areas like logic circuits, SerDes technology, and overall system design. We need to gain design experience and ensure smooth mass production. We must ensure that the dedicated engineers working tirelessly day and night receive the support they need. With AI's emergence, many applications have appeared and demand is changing fast. Memory by nature takes a long time to build fabs, install equipment, and start production. Even so, when we have the opportunity to lead, we can engage in discussions with industry frontrunners like NVIDIA. By accumulating verification techniques and expertise in this logic design, we can make significant progress once again. In the context of electronic engineering, I will explain how the concepts of parallelism and serialization, which are fundamental, can be applied to system-on-chip design. Using system-on-chip as a pretext, I've explored various related topics. This has been an error-free explanation so far.